In this video, let's address some common errors and issues from questions 9 and 10 of the problems from chapters 2 to 5. Here, some students have asked about the construction of the bifurcation diagrams, and mainly how do we know what side the arms of the bifurcation diagram curves towards about the bifurcation point. Now usually, there are two ways of doing this. First, informally in terms of the cobweb diagrams, you draw the cobweb diagrams and study the motion of the roots and intersections as the mu parameter varies. And secondly, you can do a formal local analysis near the bifurcation diagram and develop the Taylor series. When you do the second approach, you would be able to develop an approximation of the fixed points or periodic points. This may involve square root expressions from which you would draw conclusions about which side the bifurcation curves emerge. Here is an example from question 9a. The system is given by mu times sine of x. Let's focus on the positive values of mu. First, if mu is small and positive, there is only one fixed point at the origin which looks to be stable. Second, if mu is sufficiently large, the zero at the origin splits into 3 and hence a pitchfork bifurcation emerges. You can see that the rightmost fixed point is stable, but now x equal to 0 is unstable. In the bifurcation diagram, you can now draw the pitchfork bifurcation and change the center x equal to 0 line from solid to dashed. Notice that if mu is increased further, here mu is equal to 3, the gradient from the third fixed point begins to steepen. You would assume that at some stage it is -1, so the fixed point transitions from stable to unstable, producing a period doubling fixed point. Once you have confirmed this, you can then draw the period doubling bifurcation in the bifurcation diagram to the right. Finally, if mu is increased still further, here mu is equal to 8, notice that you will produce two new fixed points out of thin air. You would conclude that this is a saddle node bifurcation. It does take some thinking to check that the lower saddle node branch is unstable and the top is stable. But one key mistake is that some students didn't draw the saddle node bifurcation in a disconnected fashion with the rest of the bifurcation diagram, but it should be. It's now up to you to draw the bifurcation diagram for mu less than 0. Do this and verify that it is as it should be. Let's end with a short note on question 10a. Students have asked in what direction should I draw the arms of the period doubling bifurcations. You can answer this in one of two ways listed above. Notice that in the image, I've drawn a sketch of the arms in blue on top of the solutions in your sets. Informally, imagine beginning on the unstable arm. The idea is that you would have to go upwards in this diagram, since it's unstable, but that you can't tend towards the dashed line above, since that line is also unstable. So there must exist a curve in between where the system approaches. This is evidence that the period doubling arms would lie on the left of mu is equal to 2 rather than on the right. Secondly, if you perform the local analysis shown in the solutions, you would be able to predict that the functional form of the period doubling curves occurs as a square root. You can then verify that the square root only exists with real values for mu less than 2. This tells you that the directions of the arms tends towards the left rather than the right. A similar argument is applied to determine the direction of the arms for the bifurcation point at mu is equal to 6.